They called it a ghostly world, veiled in distance and mystery, spinning quietly at the edge of our solar system. But now Neptune, the eighth and final planet since Pluto's reclassification, has stepped out of the shadows. Thanks to the unparalleled power of the James Webb Space Telescope, or JWST, we are witnessing this icy giant like never before. And what it's revealing is both breathtaking and deeply confounding. For the first time in over 3 decades, astronomers are seeing Neptune not as a blurry blue sphere but as a dynamic, storm-swept world adorned with shimmering rings and veiled by methane-rich clouds. This isn't just a picture, it's a doorway into a realm that has long eluded our understanding. When NASA released JWST's first high-resolution image of Neptune in September 2022, it sent ripples through the scientific community. The image captured more than just a distant planet, it offered a new lens into the cosmos. For decades, our knowledge of Neptune was limited to glimpses from Voyager 2's fleeting flyby in 1989 and the limited capabilities of Hubble. But now, through JWST's near-infrared camera, and ARCam, Neptune is being reborn in extraordinary detail. We're seeing clouds of methane ice reflecting sunlight like scattered diamonds and, most astonishingly, the fine, delicate rings that have eluded clear observation for years. This is not just a visual update. It's a scientific revolution. To appreciate what's at stake, one must understand Neptune's unique role in the solar system. Orbiting at an average distance of 4.5 billion kilometers from the Sun, it takes 165 Earth years to complete just one orbit. It's the densest and third most massive of the giant planets, composed primarily of hydrogen, helium, and ices like water, ammonia, and methane, hence the classification as an ice giant. These ingredients give Neptune its haunting sapphire hue and define the planet's extreme weather systems. Winds can roar across its surface at more than 1,300 miles per hour, the fastest in our solar system, whipping up massive storms that dwarf anything seen on Earth. Neptune's discovery was itself a triumph of the human mind. In the mid-19th century, astronomers noticed strange wobbles in Uranus's orbit, ripples that suggested the gravitational pull of another body. Using nothing more than mathematics, British and French astronomers independently predicted the existence of an unknown planet. And in 1846, Johann Galle located it from the Berlin Observatory, exactly where the calculations said it would be. Neptune was the first planet discovered through math, not direct observation, a testament to the power of scientific deduction. Yet despite that auspicious beginning, Neptune has remained one of the most poorly understood planets in our solar system. Voyager 2's brief encounter showed us a world of violent weather and intriguing features like the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot. But without further missions, our understanding stagnated. Hubble's attempts to observe Neptune were impressive, but even it couldn't pierce the thick veil of its methane-laden atmosphere or resolve the planet's faint rings. Enter JWST, with its massive 6.5-meter mirror and deep infrared sensitivity. Unlike Hubble, which sees mostly invisible and ultraviolet light, JWST peers into the infrared spectrum, perfect for studying cold, distant worlds like Neptune. Methane absorbs infrared light, making the planet appear dark in JWST's images. But this darkness only enhances the visibility of high-altitude clouds, bright, glowing patches that reflect sunlight. These methane ice clouds now stand out with stunning clarity, revealing their structure and movement across the planet's surface. Even more dramatic was the revelation of Neptune's ring system. First hinted at by ground-based observations and later confirmed by Voyager 2, Neptune's rings are thin, dusty, and faint, virtually invisible without the right tools. Now, for the first time since the 1989 flyby, JWST has shown them in full glory, concentric arcs of particles encircling the distant planet, shaped by gravitational interactions with Neptune's moons. These rings are not just pretty, they're clues. Clues to the planet's history, its formation, and the dynamics of its gravitational environment. In the JWST image, we also see a delicate line tracing Neptune's equator. This feature likely marks a band of atmospheric circulation, a jet stream powered by the planet's internal heat. Unlike the gas giants Jupiter and Saturn, Neptune emits more heat than it receives from the Sun. The source of this internal energy remains one of planetary science's greatest mysteries. It's believed to contribute to the planet's extreme winds and erratic weather patterns. Another captivating discovery is a vortex at Neptune's south pole, wrapped in a halo of bright cloud bands. Such polar storms have been observed before, but never with this level of clarity. The presence of a continuous band of clouds at higher latitudes suggests a complex and multi-layered atmosphere, one in which energy and material are constantly shifting. For scientists, these cloud patterns offer vital data about temperature gradients, pressure layers, and wind speeds across Neptune's atmosphere. Beyond the planet itself, JWST's image also includes Neptune's largest moon, Triton. Appearing as a bright, spiky point of light, Triton shines with reflected sunlight and exhibits diffraction spikes, a result of JWST's optics. Triton is a fascinating object in its own right, believed to be a captured Kuiper belt object, orbiting Neptune in a retrograde direction. It may harbor a subsurface ocean and even shows signs of cryovolcanism. Seeing Triton in the same frame as Neptune invites comparison and raises compelling questions about the history of the Neptunian system. So what does all this mean for the future? For one, these high-resolution images mark a new era in outer planet exploration. With this level of detail, scientists can now monitor Neptune's weather over time, track atmospheric changes, and even look for seasonal shifts. It also reignites interest in returning to the outer solar system. Missions like the proposed Neptune Odyssey, still in conceptual stages, may soon gain traction. Such a mission could orbit Neptune, study Triton up close, and even deploy atmospheric probes. But beyond the data and the scientific milestones, JWST's image of Neptune represents something even more profound. It reminds us that exploration doesn't always require proximity. That even from 4.5 billion kilometers away, we can see deeply, clearly, and beautifully into a world that once felt beyond reach. The telescope's eye, perched a million miles from Earth at the L2 Lagrange point, peers into the abyss and brings back visions that redefine what we know, and what we dream. In the age of digital stars and AI horizons, Neptune's ghostly rings shimmer not just as planetary features but as beacons. They whisper that there's still so much left to learn. That beyond each discovery lies another mystery, waiting silently in the deep. And for now, JWST is just getting started. Stay with us as we continue this incredible journey in Part 2, where we explore Triton in more detail, dive into the possibility of a hidden subsurface ocean, and ask, could Neptune's system hold secrets about the origin of water in our solar system, or even the building blocks of life? They called it the edge of the unknown, a world cloaked in storms and ice, turning silently through the void some 4.5 billion kilometers from the warmth of the sun. And now, for the first time, we're not just guessing what lies beneath Neptune's swirling atmosphere, we're beginning to see it. As Part 2 of this cosmic journey unfolds, the image from the James Webb Space Telescope was only the beginning. Because what it unveiled, the jet streams, the rings, the storm systems, is now igniting a broader movement in planetary science. The urgency for a dedicated Neptune mission has never been stronger. For decades, the solar system's eighth planet was the forgotten giant. Jupiter had Juno. Saturn had Cassini. Uranus and Neptune? Left to Voyager's aging snapshots and the occasional glance from Hubble. But the insights from JWST have reopened the case file on Neptune, starting with its ferocious and short-lived storms. Unlike Jupiter's Great Red Spot, which has endured for centuries, Neptune's Great Dark Spot vanished just 5 years after Voyager 2 observed it. Hubble tried to find it in 1994, only to discover it had disappeared. Another storm later formed in Neptune's northern hemisphere, only to fade again within a few years. These ephemeral storms reveal a fundamental truth. Neptune's atmosphere is not only dynamic, it's wildly unstable. Some researchers now believe these storms don't truly vanish. Instead, they might continue swirling in Neptune's deeper atmospheric layers, only resurfacing when the right pressure and temperature conditions align. The storms we see, then, could be just the tip of something more powerful churning far below the visible clouds. In 2020, Hubble witnessed something extraordinary. A massive storm in Neptune's northern hemisphere, wider than the entire Atlantic Ocean, began migrating toward the equator. According to every existing model, this storm should have dissipated. But instead, it reversed course and drifted back toward the north, defying expectations. Such behavior had never been observed before on any planet. It's as if Neptune's atmosphere is governed by a logic all its own, teasing scientists with patterns that rewrite our textbooks every time we look. And these aren't small tempests. One of Neptune's largest storms measured 4,600 miles across, larger than Earth. But to understand what drives these colossal forces, scientists agree, we need to go back. Not with telescopes, but with machines designed to survive Neptune's brutal conditions. A dedicated probe, perhaps similar to the Galileo or Cassini missions, could descend into the atmosphere itself, measuring pressure, temperature, composition, and wind speeds in real time. Only then can we decode the chaotic ballet of storms raging beneath Neptune's icy haze. But Neptune doesn't guard its secrets alone. Orbiting in defiance is Triton, its largest moon, a mystery almost as profound as the planet itself. Unlike any other major moon in the solar system, Triton travels in the opposite direction of Neptune's rotation, a retrograde motion that screams of a violent past. Triton, scientists believe, was once a Kuiper belt object, an icy world born far from the Sun and later captured by Neptune's gravity. That capture likely disrupted Neptune's original moon system, causing ancient satellites to crash, fragment, or be flung into space. But Triton isn't just a relic, it's active. When Voyager 2 passed by in 1989, it caught glimpses of something astonishing: geysers hundreds of kilometers tall, erupting nitrogen into space. Cryovolcanism, ice volcanoes that spew frozen material instead of molten rock, was happening in real time. Triton, in the freezing twilight of the solar system, was alive. Its surface is hauntingly smooth, devoid of impact craters, suggesting recent geological resurfacing. That resurfacing, scientists suspect, might be powered by tidal heating, the same gravitational forces that stir up volcanic activity on Jupiter's moon Io or maintain subsurface oceans on Europa and Enceladus. And yes, Triton may harbor a liquid ocean beneath its crust. If true, that would make it one of the few confirmed ocean worlds beyond Earth, a tantalizing prospect in the search for extraterrestrial life. Imagine what a lander could find. An orbiter mapping Triton's terrain in detail. A probe melting through its icy surface into the liquid depths below. The chemistry of that hidden ocean might hold not only the secrets of Triton's past but clues to the broader question: how common are habitable environments in the universe? And Triton is just one of 14 known moons. Neptune's satellite system is a hodgepodge of irregular orbits and captured bodies, survivors of gravitational chaos. Among them is Nereid, which follows one of the most eccentric orbits in the solar system, swinging between extremes of distance and speed. Such oddities tell a story of a system that was disrupted, rearranged, and never quite settled again. A probe could track these moons, catalog their compositions, map their surfaces, and reconstruct the cosmic drama that shaped them. All of this, Neptune's atmosphere, Triton's potential ocean, the bizarre moons, points to a glaring gap in space exploration. There is still no dedicated Neptune mission. But that might change. The Neptune Odyssey, a proposed flagship mission from NASA, is now gaining momentum. If approved, it could launch in the 2030s, arriving decades later to orbit the planet, drop atmospheric probes, and deploy a Triton lander. Such a mission would be monumental, the outer solar system's next great leap. Until then, JWST continues to be our silent sentinel, capturing faint reflections and ghostly shadows from billions of kilometers away. Each new image sharpens our vision of Neptune, reminding us that this frozen giant is anything but inert. Stormy, moody, active, and utterly alien. These discoveries also force us to reflect on our place in the solar system. Neptune is not just another distant planet. It's a time capsule from the solar system's earliest days, a guardian of secrets about planetary formation, atmospheric chemistry, and perhaps even the origins of life itself. As our tools improve and our questions grow deeper, Neptune stands waiting, unchanged and unbothered, holding tight to answers we are only just beginning to understand. For the scientists chasing these answers, and for the dreamers who look up with wonder, Neptune is no longer just a blue blur at the edge of maps. It's a frontier, a laboratory, a challenge, and soon, perhaps, a destination. So as we look outward with new eyes, let us not forget that beyond every telescope lens is a question, and beyond every question, a story. Neptune's is one of storms and ice, of captured moons and vanished mysteries. And one day we'll go there, not just with our vision but with our machines, our questions, and our unending human curiosity. Because in the silence of Neptune's deep, there is still a voice calling. And we are finally beginning to listen. And as technology progresses, so does our ability to answer that call. With every step forward in propulsion systems, AI-controlled probes, and radiation-hardened instruments, the idea of a Neptune mission shifts from fantasy to feasibility. European space agencies, too, are expressing growing interest in collaboration, understanding that such a mission would push the limits of engineering, endurance, and global cooperation. Neptune might be far, but the will to reach it is closer than ever. The significance of exploring Neptune isn't confined to academic curiosity. What we learn there could help us understand exoplanets, distant worlds that resemble Neptune in size and composition. Many of the gas and ice giants discovered outside our solar system are Neptune-like, meaning our own Neptune may serve as a baseline model for studying the characteristics, formation, and potential habitability of alien worlds across the galaxy. Ultimately, the questions we ask of Neptune are the same questions that have fueled exploration for centuries. What lies beyond? How did it all begin? And might we not be alone after all? Neptune's answers will come not in one burst, but slowly through patient science and determined engineering. And in the vast dark that stretches between us and that distant blue dot, hope travels silently, on radio waves, on photon collectors, on dreams that refuse to die. We are explorers still. And Neptune, icy, storm-ridden, mythic, is waiting for us to arrive.